Let's compare the energy, frequency, and wavelengths of various photons. To help us, we will use figure 2.2 from the textbook, which is shown here. Notice that in the middle of the figure, different types of light are shown using their common names. The visible portion of the spectrum has been blown up and shown at the bottom. Note, however, that the visible region actually only occupies a narrow rainbow-colored band between infrared and ultraviolet. This can be confusing when comparing the different types of light. At the top are the different wavelengths in meters that go along the x-axis of the figure. Just below that are the corresponding frequencies. Notice that on going from left to right, the wavelengths are getting smaller while the frequencies are getting larger. This is the inverse proportionality we expect from the relationship C equals lambda nu. Since the larger frequencies are at the right-hand side of the figure, that is also the location of the greater energy photons. This is the direct proportionality we expect from the relationship E equals h nu. Remembering these two relationships will help us rank photons. For example, if we ask, which has the greater wavelength, microwaves or ultraviolet light? We can see that microwaves are centered at a wavelength of about 10 to the minus 2 meters, or in the centimeter range, while ultraviolet light is centered at a wavelength of about 10 to the minus 8 meters, or in the tens of nanometers. Microwaves have the greater wavelength. If we ask which has the greater frequency, red light or infrared light, we can see that all visible light has a frequency between 10 to the 14th and 10 to the 15th per second, whereas infrared light is centered around 10 to the 13th per second. Red light would have a greater frequency. Even without the figure, we should be able to rank photons in energy, frequency, and wavelength, knowing just one of the relationships. For example, which has the greater energy? Light with a frequency of 6 times 10 to the 8th per second, or light with a frequency of 2 times 10 to the 14th per second? We should recognize that seconds to the minus 1 is the unit of frequency. Since energy and frequency are directly proportional, the light with the greater frequency will also have the greater energy. Which has the greater or longer wavelength? A photon of 6 times 10 to the minus 14th joules, or a photon at 6 times 10 to the minus 18th joules? Remember that joules is a unit of energy. While frequency and energy are directly proportional to each other, they are inversely proportional to wavelength. The greater wavelength photon will have the smaller energy.